Hello there, and welcome to the Psyche's Rest channel. Tonight, we're going to explore one of the most fascinating and remarkable processes that occurs while we sleep, the consolidation of memory. Every night, as you rest peacefully, your brain is performing an extraordinary service for you, working diligently to organize, strengthen, and store the memories of your day. This nocturnal memory work is one of the most important functions of sleep, yet it happens largely outside our conscious awareness. Think about all the things you learned and experienced today, the conversations you had, the places you visited, the information you absorbed, the skills you practiced, the emotions you felt. Each of these experiences created fragile traces in your brain, like footprints in sand, easily erased unless something more permanent is done to preserve them. Sleep is the gentle sculptor that transforms these fragile impressions into lasting memories that you can recall days, weeks, or even years later. The relationship between sleep and memory is one of the most well-documented phenomena in neuroscience research. For decades, scientists have observed that people who learn new information and then get good quality sleep tend to remember that information better than those who are sleep deprived. This observation holds true across all kinds of learning, from academic subjects to motor skills, from emotional experiences to factual knowledge. Sleep appears to be essential for converting short-term, fragile memories into long-term, stable ones. What makes this process so fascinating is how elegantly our brain systems have evolved to perform this vital work during the hours when we're not actively engaged with the external world. While we're asleep, our brain is freed from the constant influx of new sensory information and can focus its resources on the important work of memory maintenance. It's as if the brain uses the quiet of night to organize the library of our experiences, deciding which books to keep on permanent display and which to store in the archive. From a psychological perspective, understanding how sleep consolidates memory can help us appreciate the importance of good sleep hygiene and develop more effective learning strategies. It might change how you approach studying, problem solving, or processing emotional experiences. It reminds us that learning doesn't end when we close the book or step away from the computer. The brain continues processing and consolidating information long after we've stopped consciously thinking about it. As we explore this topic together tonight, you might find yourself developing a greater appreciation for the work your brain does while you sleep. You might think differently about your own learning processes, perhaps choosing to respect your brain's need for rest rather than pushing through fatigue. And if you find these explorations of psychology and sleep helpful for your own rest, you're welcome to like and subscribe to the channel. But for now, simply settle in, let your breathing become calm and regular, and allow yourself to wonder about the remarkable memory work your brain will perform tonight. Throughout our journey tonight, we'll maintain a tone of gentle exploration and wonder. The processes of memory consolidation during sleep are complex and involve sophisticated neural mechanisms, but we'll approach them with curiosity rather than complexity, focusing on understanding the broader patterns and their implications for our daily lives. We'll look at what current research has revealed about how sleep strengthens memories, while always remembering that this is still an active area of scientific investigation with many questions yet to be fully answered. Before we begin our exploration, it's worth noting that while this discussion is educational and informative, it's not a substitute for professional medical advice. If you have concerns about your sleep patterns or memory function, consulting with healthcare professionals is always recommended. Our goal here is to provide understanding and perspective on the fascinating processes that occur during sleep, not to diagnose or treat any conditions. Let's start by understanding what we mean by memory consolidation and why it's so crucial for our ability to learn and remember. Memory consolidation refers to the process by which a short-term, fragile memory trace is gradually transformed into a more stable, long-term memory. This process involves several key changes to how memories are stored in the brain, making them more resistant to interference and more accessible for future recall. When we first experience something new, whether it's hearing a fact, learning a skill, or having an emotional experience, the memory is initially stored in a fragile, temporary state. This initial memory trace is vulnerable to disruption and can be easily lost if not properly consolidated. Think of it like taking a photograph with a Polaroid camera. The image appears initially, but needs time to develop fully and become permanent. The consolidation process involves several important changes to the memory trace. First, the memory becomes more stable and less vulnerable to interference. Second, it becomes integrated with existing knowledge and memories, creating meaningful connections that make it easier to recall later. Third, the memory may become less detailed and more abstract, capturing the essential meaning while discarding irrelevant details. Finally, the memory becomes more accessible through neural pathways that make it easier to retrieve when needed. Research has shown that different types of memories undergo consolidation through somewhat different processes and at different rates. Declarative memories, facts and events that can be consciously recalled, tend to consolidate relatively quickly, often within hours or days of initial learning. Procedural memories, skills and habits that are expressed through performance rather than conscious recall, may take longer to fully consolidate and may benefit from repeated practice over days or weeks. The timing of memory consolidation is also important. Researchers have found that sleep soon after learning can be particularly beneficial for memory consolidation. This suggests that there might be optimal windows of time when the brain is most receptive to consolidating new memories. This has practical implications for learning strategies. It might be more effective to study in the evening and then get a good night's sleep than to study late into the night and then get only a few hours of rest. The relationship between sleep and memory consolidation becomes particularly interesting when we consider the different stages of sleep. Research has revealed that different stages of sleep appear to play different roles in the consolidation of different types of memories. This suggests that the brain has evolved sophisticated mechanisms for matching specific types of memory work to specific sleep states, optimizing the overall efficiency of memory consolidation. The discovery that sleep plays a crucial role in memory consolidation represents one of the most important findings in sleep science. Before this research emerged, many people thought of sleep as simply a passive state of rest. We now understand that sleep is an active, dynamic process that serves essential cognitive functions, with memory consolidation being perhaps the most important of these functions. Historically, the relationship between sleep and memory has been observed for centuries. Even in ancient times, people noted that sleeping on a problem could lead to creative insights or solutions. The saying, "let me sleep on it," reflects the intuitive understanding that sleep can help with cognitive processing and decision-making. However, it's only in recent decades that we've begun to understand the specific neural mechanisms that underlie these observations. One of the earliest scientific investigations into sleep and memory came from research on dream interpretation in the early 20th century. While the initial theories about dream meaning were largely speculative, these studies led to more systematic investigations into how sleep affects cognitive processes. Later research in the 1,950 seconds and 1,960 seconds, with the discovery of REM sleep, opened up new avenues for understanding the relationship between sleep and mental functions. The modern era of sleep and memory research really began in the 1,970 seconds and 1,980 seconds, with the development of more sophisticated techniques for studying both sleep and memory. Researchers began to systematically test how sleep affects memory performance by having people learn new information and then either allowing them to sleep or keeping them awake. The results consistently showed that sleep enhanced memory performance, leading to the hypothesis that sleep plays an active role in memory consolidation. The 1,990 seconds saw significant advances in our understanding of the neural mechanisms of memory consolidation during sleep. The development of more advanced neuroimaging techniques allowed researchers to observe brain activity during sleep, revealing that the brain is far from inactive during this time. These studies showed that brain regions involved in memory processing, particularly the hippocampus, are highly active during sleep, suggesting that the brain is actively working on memory consolidation rather than simply resting. More recent research has focused on understanding the specific neural processes that occur during memory consolidation in sleep. Studies using techniques like single-unit recording in animals have revealed that neurons in memory-related brain regions often replay patterns of activity that occurred during waking experiences. This neural replay appears to be a key mechanism for strengthening memory traces during sleep. The field of sleep and memory research continues to evolve and grow, with new discoveries constantly expanding our understanding of this fascinating process. Researchers are now exploring how different types of memories are processed during different stages of sleep, how emotional memories are handled during sleep, and how memory consolidation changes across the lifespan. Each new discovery reveals more about the remarkable efficiency and complexity of the brain's memory systems. Understanding memory consolidation during sleep has important practical implications for many areas of life. In education, it suggests that the timing of learning activities relative to sleep could significantly affect learning outcomes. In clinical settings, it provides insights into how sleep disorders might affect memory function and how improving sleep quality might help with memory-related conditions. In everyday life, it reminds us of the importance of getting adequate sleep for optimal cognitive performance. As we continue our exploration of how sleep consolidates memory, we'll delve deeper into the neuroscience of this process, examining the specific brain regions and neural mechanisms involved. We'll explore how different stages of sleep contribute to different types of memory consolidation, how emotional memories are processed during sleep, and how this remarkable process changes throughout our lives. By understanding these processes, we can develop greater appreciation for the work our brains do while we sleep and make more informed decisions about how we learn and rest. The neuroscience of memory formation represents one of the most fascinating areas of brain science. Understanding how our brains initially encode experiences and how these memories are later consolidated during sleep reveals the extraordinary complexity and efficiency of our cognitive systems. The process of memory formation involves multiple brain regions working together in coordinated fashion, creating and storing the traces of our experiences that will later become the foundation of our knowledge and abilities. Memory formation begins the moment we experience something new. Whether we're listening to a lecture, having a conversation, learning a new skill, or experiencing an emotional event, our brain is actively working to encode that experience into memory. This initial encoding process involves several key brain regions working together to capture the various elements of the experience and create a coherent memory trace. The hippocampus, a seahorse-shaped structure deep in the temporal lobe, plays a central role in the initial encoding of new memories. This remarkable brain structure acts as a temporary storage system for new experiences. Receiving input from various sensory and emotional processing areas of the brain and integrating this information into a coherent memory trace. The hippocampus is particularly important for declarative memories, facts and events that we can consciously recall and describe. When we experience something new, sensory information from our eyes, ears, and other senses travels to the appropriate processing areas of the cortex. Visual information goes to the visual cortex, auditory information to the auditory cortex, and so on. These sensory processing areas then send the processed information to the hippocampus, where it's integrated with emotional information from the amygdala and contextual information from other brain regions. This integration process is remarkably efficient. The hippocampus can bind together different elements of an experience, what we saw, heard, felt, and thought, into a single coherent memory trace. This binding process involves creating connections between neurons that represent different aspects of the experience, forming neural networks that will later allow us to retrieve the entire memory when we encounter related cues. The initial encoding of a memory involves changes in the strength of connections between neurons, a process known as synaptic plasticity. When neurons fire together during an experience, the connections between them become stronger through a process called long-term potentiation. This strengthening of synaptic connections is thought to be the cellular basis of memory formation, creating the physical changes in the brain that represent the memory trace. However, these initial changes are fragile and temporary. Without further processing, the memory trace remains vulnerable to disruption and may fade away completely over time. This is where sleep becomes crucial. During sleep, particularly during slow-wave sleep, the brain reactivates and strengthens these neural connections, transforming the fragile initial memory trace into a more stable, long-term memory. The process of memory formation also involves different types of memory systems in the brain. Working memory, which allows us to hold and manipulate information over short time periods, involves primarily the prefrontal cortex. Short-term memory, which can hold information for slightly longer periods, involves temporary changes in neural activity patterns. Long-term memory which can store information for extended periods, involves structural changes in neural connections. The transition from short-term to long-term memory is a gradual process that involves multiple stages of consolidation. Immediately after an experience, the memory trace is primarily stored in the hippocampus. Over time, through processes that occur during both wakefulness and sleep, the memory gradually becomes stored in the cortex as well, a process called systems consolidation. This systems consolidation process is particularly important for understanding how sleep affects memory. During sleep, particularly during slow wave sleep, the hippocampus and cortex communicate in ways that facilitate the transfer of information from temporary hippocampal storage to more permanent cortical storage. This transfer allows the memory to become independent of the hippocampus and integrated with existing knowledge stored in the cortex. The initial encoding of a memory is also influenced by factors like attention, emotion, and prior knowledge. When we pay close attention to something, we're more likely to encode it strongly into memory. Emotional experiences tend to be encoded more strongly than neutral ones, due to the involvement of the amygdala and its connections to the hippocampus. Information that relates to what we already know is typically easier to encode than completely novel information. The quality of initial encoding can affect how well the memory consolidates during sleep. Strong initial encoding leads to more robust memory traces that are more likely to be effectively consolidated during sleep. This suggests that factors that affect attention, emotion, and prior knowledge during initial learning can indirectly affect how well memories are consolidated during subsequent sleep. The process of memory formation also involves different types of memories with different properties and consolidation requirements. Episodic memories are memories of specific events from our personal past, including when and where they occurred. Semantic memories are general knowledge and facts about the world that aren't tied to specific personal experiences. Procedural memories are skills and habits that are expressed through performance rather than conscious recall. Each of these types of memories involves somewhat different brain regions and consolidation processes. Episodic memories heavily involve the hippocampus, particularly during initial encoding and early consolidation. Semantic memories involve more distributed networks in the cortex and may not require as much hippocampal involvement, especially for well-established knowledge. Procedural memories involve structures like the basal ganglia and cerebellum and may consolidate through somewhat different mechanisms than declarative memories. The timing of memory consolidation is also important. Research has shown that there are optimal windows for memory consolidation, with some evidence suggesting that consolidation is particularly effective during certain phases of the sleep cycle. The first few hours of sleep, particularly slow-wave sleep, appear to be especially important for consolidating memories learned during the day. The process of memory formation during wakefulness also prepares memories for later consolidation during sleep. Studies have shown that experiences that are followed by periods of rest, even brief ones, tend to be better remembered than experiences that are immediately followed by new learning. This suggests that the brain begins the consolidation process even before sleep, though sleep appears to be when the most intensive consolidation work occurs. Understanding the neuroscience of memory formation helps us appreciate the complexity of the processes that occur during sleep. When we understand that our brains have been working all day to capture and temporarily store our experiences, we can better appreciate the importance of providing adequate time during sleep for the consolidation work to continue. This understanding can help us make more informed decisions about how we structure our learning activities and our sleep schedules. As we continue to explore how sleep consolidates memory, we'll examine the specific roles that different sleep stages play in this process, how different types of memories are handled differently during sleep, and how this remarkable process changes throughout our lives. By understanding these processes, we can develop greater appreciation for the cognitive work our brains perform while we sleep and develop more effective strategies for learning and remembering. The relationship between sleep stages and memory types reveals one of the most fascinating aspects of how our brains process information during rest. Sleep is not a uniform state, but rather cycles through different stages, each with its own patterns of brain activity and its own particular functions for memory consolidation. Understanding how different sleep stages contribute to different types of memory processing can help us appreciate the sophisticated coordination that occurs in our brains each night. Sleep is typically divided into two main types: REM rapid eye movement, sleep, and NREM non-rapid eye movement, sleep. NREM sleep itself is divided into three stages: N1, N2, and N3, with N3 being the deepest stage, often called slow wave sleep due to the characteristic slow brain waves that occur during this stage. Each complete sleep cycle typically lasts about 90 to 110 minutes and includes multiple stages of both NREM and REM sleep. NREM sleep, particularly slow wave sleep, N3, appears to be especially important for the consolidation of declarative memories, facts, and events that we can consciously recall and describe. During slow wave sleep, the brain produces slow, synchronized oscillations of electrical activity that appear to facilitate the transfer of information from the hippocampus to the cortex. This transfer is crucial for systems consolidation, the process by which memories become independent of the hippocampus and integrated with existing knowledge in the cortex. Research has shown that slow wave sleep is particularly important for consolidating spatial memories and memories that require careful attention during initial encoding. Studies have found that the amount of slow wave sleep after learning predicts how well those memories will be remembered later. Additionally, disruption of slow wave sleep, whether through sleep deprivation or experimental interference, can impair memory consolidation. REM sleep, characterized by rapid eye movements, muscle atonia, and brain activity patterns that resemble wakefulness, appears to play a different but equally important role in memory consolidation. REM sleep seems particularly important for procedural memories, skills, and habits that are expressed through performance rather than conscious recall. It may also play a role in the consolidation of emotional memories and in creative problem solving. The role of REM sleep in procedural memory consolidation has been demonstrated in numerous studies. People who learn motor skills, such as playing a musical instrument or participating in sports, tend to show improved performance after a night of sleep that includes adequate REM sleep. Studies have also shown that REM sleep deprivation can interfere with the consolidation of these procedural memories. REM sleep may also play a role in emotional memory processing. During REM sleep, the amygdala, which processes emotions, is highly active, while the prefrontal cortex, which regulates emotions, is relatively less active. This pattern of activity may allow for the processing of emotional memories while reducing their emotional intensity, helping us remember important emotional events without being overwhelmed by the associated emotions. The coordination between different sleep stages for memory consolidation is quite sophisticated. Typically, slow-wave sleep dominates the first half of the night, while REM sleep becomes more prevalent in the second half. This timing may reflect an optimal arrangement for memory consolidation, with slow-wave sleep consolidating declarative memories learned during the day, followed by REM sleep processing other types of memories and integrating the newly consolidated information with existing knowledge. The cycling between different sleep stages may also serve a protective function for memory. By alternating between different states of brain activity, the brain can work on different types of memory processing during different stages, ensuring that all types of memories receive appropriate consolidation work. This cycling might also help prevent interference between different types of memories or between new memories and existing knowledge. Sleep spindles, brief bursts of brain activity that occur during N2 sleep, also appear to play a role in memory consolidation. These spindles are thought to facilitate the communication between the hippocampus and cortex, potentially helping to coordinate the transfer of information between these brain regions. Research has shown that the number of sleep spindles during the night correlates with memory performance on tasks learned the previous day. The timing of learning relative to the sleep cycle can also affect how memories are consolidated. Studies have shown that learning immediately before sleep can lead to particularly effective consolidation, possibly because the memory traces are fresh and still active when sleep begins. Learning early in the day, followed by a full night of sleep, also tends to result in good consolidation, suggesting that there may be multiple optimal windows for memory consolidation during sleep. The relationship between sleep stages and memory types becomes even more complex when we consider that different types of memories may be processed differently during different sleep cycles across the night. Some research suggests that earlier sleep cycles might be more important for consolidating certain types of memories, while later cycles might be more important for others. This could explain why getting a full night of sleep with multiple sleep cycles is often more beneficial for memory than getting the same total amount of sleep in fragmented periods. The role of naps in memory consolidation also reflects the importance of specific sleep stages. Short naps that include both NREM and REM sleep tend to be more beneficial for memory consolidation than naps that include only one type of sleep. This suggests that the full sequence of sleep stages may be important for optimal memory processing, even in shorter sleep periods like naps. As we age, the patterns of sleep stages change, with older adults typically experiencing less slow-wave sleep and more fragmented sleep. These changes in sleep architecture may contribute to the memory changes that occur with aging, suggesting that maintaining healthy sleep patterns throughout life is important for cognitive function. The study of how different sleep stages contribute to memory consolidation continues to reveal new insights into the sophisticated coordination of brain processes during sleep. Each stage of sleep appears to make its own unique contribution to memory processing, working together with the other stages to ensure that all types of memories receive appropriate consolidation work. This coordination represents one of the most remarkable examples of the efficiency and complexity of brain function. Understanding the roles of different sleep stages in memory consolidation can help us appreciate the importance of getting adequate, high-quality sleep. It suggests that our brains have evolved sophisticated mechanisms for maximizing the benefits of sleep for cognitive function, with different sleep stages working together like a well-orchestrated team to ensure that all types of memories are properly processed and stored. The hippocampus and memory replay represent one of the most fascinating mechanisms of memory consolidation during sleep. During sleep, particularly during slow-wave sleep, neurons in the hippocampus spontaneously reactivate patterns of activity that occurred during waking experiences. This neural replay is thought to be a crucial mechanism for strengthening memory traces and transferring information from temporary hippocampal storage to more permanent cortical storage. The discovery of neural replay during sleep represents one of the most important breakthroughs in sleep and memory research. Scientists found that when animals ran through a maze during the day, their hippocampal neurons would later fire in the same sequences while they slept. This replay occurred during slow-wave sleep and was temporally compressed. The entire maze run might be replayed in just a few seconds of sleep. This neural replay phenomenon suggests that the brain is actively practicing or rehearsing experiences during sleep, strengthening the neural connections that represent those experiences. The replay isn't exact, but rather seems to capture the essential patterns and sequences of the original experience, focusing on the most important aspects of the memory trace. The role of neural replay in memory consolidation is supported by several lines of evidence. Studies have shown that disrupting neural replay during sleep impairs memory consolidation. Additionally, the amount of neural replay that occurs during sleep predicts how well memories are remembered later. This suggests that replay isn't just an epiphenomenon, but actually serves a crucial function in memory consolidation. Sharp wave ripples are brief, high-frequency oscillations that occur in the hippocampus during slow-wave sleep. These ripples are thought to coordinate the replay of memory traces and facilitate communication between the hippocampus and cortex. Research has shown that sharp wave ripples often occur immediately before neural replay events, suggesting that they might help trigger or organize the replay process. Place cells in the hippocampus provide another fascinating insight into how spatial memories are processed during sleep. These specialized neurons fire in specific locations, creating a cognitive map of the environment. During sleep, place cells often replay the sequences of locations that were experienced during waking, effectively helping to consolidate spatial memories. The timing of neural replay events is also intriguing. Research has shown that replay often occurs in bursts, with multiple replay events happening in close succession. This clustering of replay events might reflect the brain's efforts to efficiently consolidate multiple related memories, possibly by linking together experiences that occurred close together in time. The content of replay events can also provide insights into how memories are processed during sleep. Some research suggests that replay may prioritize certain aspects of experiences over others, perhaps focusing on the most important or novel elements of a memory. This selective replay might help ensure that the most crucial aspects of memories are strongly consolidated. Neural replay may also play a role in memory integration. the process of connecting new memories with existing knowledge. When replay events occur, they might activate related neural networks in the cortex, helping to link new memories with existing information. This integration process could help explain how we're able to incorporate new learning into our broader understanding of the world. The hippocampus-cortical dialogue that occurs during memory consolidation represents another important aspect of this process. While the hippocampus is initially crucial for forming new memories, long-term storage of memories increasingly depends on cortical regions. During sleep, particularly slow-wave sleep, there appears to be coordinated activity between the hippocampus and cortex that facilitates the transfer of information from hippocampal to cortical storage. This hippocampus-cortical dialogue is coordinated by neural oscillations, particularly slow oscillations in the cortex and sharp wave ripples in the hippocampus. The slow oscillations provide temporal windows that allow the hippocampus to influence cortical activity, while the sharp wave ripples coordinate the replay of specific memory traces. This coordination ensures that the right information is transferred at the right time. The process of transferring memories from hippocampus to cortex is called systems consolidation. This process typically occurs over hours to days after initial learning, with sleep playing a crucial role. During systems consolidation, memories become less dependent on the hippocampus and more integrated with cortical networks. This integration allows memories to become more stable and accessible for long-term storage. Theories of hippocampus-cortical dialogue suggest that this process might involve more than just simple transfer of information. Some researchers propose that the hippocampus might be teaching the cortex how to store and retrieve certain types of memories, essentially training cortical networks to take over memory functions. This teaching process might involve repeated coordination between hippocampal and cortical activity during sleep. The relationship between neural replay and dreaming is another fascinating area of investigation. Some researchers suggest that the content of dreams might reflect, at least in part, the neural replay that occurs during sleep. While this connection is speculative, it offers an intriguing possibility that our dreams might be a subjective experience of the memory consolidation processes that are occurring in our brains. The study of neural replay during sleep has practical implications for learning and memory. Some research suggests that certain factors can enhance neural replay, such as targeted memory reactivation techniques that present cues related to learned information during sleep. These techniques might potentially enhance memory consolidation by facilitating more extensive neural replay. The discovery of neural replay during sleep has transformed our understanding of how memories are consolidated. Rather than viewing sleep as a passive state of rest, we now understand it as an active period of memory processing, during which the brain is actively working to strengthen and integrate new experiences. This active processing during sleep might be just as important for memory as the initial encoding during wakefulness. As we continue to explore how sleep consolidates memory, we'll examine how emotional memories are processed during sleep, how procedural and skill memories are enhanced through rest, and how sleep helps us determine which memories to keep and which to let go. By understanding these processes, we can develop greater appreciation for the remarkable memory work our brains perform while we sleep. Emotional memory processing during sleep represents one of the most important and fascinating aspects of memory consolidation. Our experiences are rarely neutral. They come with emotional coloration that affects how we remember them and how they influence our future behavior. Sleep appears to play a crucial role in processing these emotional memories, helping us preserve the important information while reducing the emotional intensity that might otherwise be overwhelming. The amygdala, an almond-shaped structure deep in the temporal lobe, plays a central role in emotional memory processing. This brain region is particularly important for detecting and responding to emotionally significant stimuli and for attaching emotional significance to memories. During wakefulness, the amygdala works closely with the hippocampus to ensure that emotionally important experiences are strongly encoded into memory. During sleep, particularly REM sleep, the amygdala remains highly active, while the prefrontal cortex, which regulates emotional responses, is relatively less active. This pattern of activity, high emotional processing, combined with reduced emotional regulation, creates a unique environment for processing emotional memories. The brain can work on emotional memories while being somewhat protected from the full intensity of the emotions associated with those memories. This pattern of brain activity during REM sleep might serve several important functions for emotional memory processing. It might allow the brain to process and integrate emotional memories without becoming overwhelmed by the emotions. It might also help to reduce the emotional intensity of memories over time, allowing us to remember important events without being continually re-experiencing the full emotional impact. Research has shown that sleep can reduce the emotional intensity of memories while preserving their factual content. In studies where participants view emotionally charged images and then either sleep or stay awake, those who sleep typically show reduced emotional responses to the images when viewing them again later, while still remembering the images themselves. This suggests that sleep helps to decouple the factual and emotional components of memories. The process of emotional memory processing during sleep might be particularly important for traumatic or highly stressful experiences. While these experiences need to be remembered, their emotional intensity can be overwhelming if not properly processed. Sleep may provide a natural mechanism for processing these difficult emotions in a safe environment, reducing their intensity over time while preserving the important information contained in the memories. The timing of emotional memory processing during sleep is also important. Research suggests that REM sleep, which tends to be more prevalent in the second half of the night, might be particularly important for emotional memory consolidation. This timing might reflect an adaptive arrangement, allowing the brain to first consolidate neutral information during slow-wave sleep in the first half of the night, then process emotional information during REM sleep in the second half. Sleep also appears to play a role in fear extinction learning. The process of learning that previously feared stimuli are now safe. Studies have shown that sleep after fear extinction training can enhance the consolidation of the extinction memory, leading to reduced fear responses when encountering the feared stimulus later. This suggests that sleep might be particularly important for therapeutic approaches to anxiety and phobias. The processing of emotional memories during sleep might also contribute to mood regulation. By processing difficult emotions during sleep, we might wake up with better emotional balance and the ability to approach the day with greater emotional resilience. This could explain why a good night's sleep often leads to better mood and emotional stability the following day. Dreaming might play a role in emotional memory processing during sleep. While dreams are often strange and seemingly random, some researchers suggest that they might reflect, at least in part, the brain's attempts to process emotional experiences. The sometimes bizarre or symbolic nature of dreams might represent the brain's efforts to work with emotional memories in a safe, protected environment. The relationship between sleep and emotional memory processing becomes particularly important when considering stress and trauma. People who have experienced traumatic events often experience disturbances in sleep, particularly in REM sleep. These sleep disturbances might reflect the brain's efforts to process the traumatic memories, even if this processing is disrupted or incomplete. The processing of emotional memories during sleep might also change across the lifespan. Children's emotional memory systems are still developing, and their sleep patterns differ from those of adults. These differences might affect how emotional memories are processed during sleep at different ages. Similarly, older adults may experience changes in both emotional processing and sleep architecture that affect how emotional memories are consolidated. Understanding how sleep processes emotional memories can have important implications for mental health and well-being. Poor sleep quality or insufficient sleep might impair the processing of emotional memories, potentially leading to emotional dysregulation or mood disorders. Conversely, addressing sleep problems might help improve emotional regulation and reduce symptoms of mood disorders. The study of emotional memory processing during sleep continues to reveal new insights into how our brains work to balance the need to remember important emotional experiences with the need to protect ourselves from being overwhelmed by emotions. This delicate balance represents one of the most sophisticated aspects of human cognition and emotion. As we continue to explore how sleep consolidates memory, we'll examine how procedural and skill memories are enhanced through rest, how sleep helps us determine which memories to keep and which to let go, and how these processes change throughout our lives. By understanding these processes, we can develop greater appreciation for the remarkable work our brains perform while we sleep. Procedural and skill memory represents another fascinating category of memory that benefits significantly from sleep consolidation. Unlike declarative memories, which involve facts and events that we can consciously recall, procedural memories are skills and habits that are expressed through performance. Things we know how to do but can't necessarily explain in words. Examples include riding a bike, playing a musical instrument, typing, or performing sports movements. The consolidation of procedural memories during sleep appears to follow somewhat different principles than declarative memory consolidation. While declarative memories rely heavily on the hippocampus for initial encoding and early consolidation, procedural memories involve different brain regions like the basal ganglia, cerebellum, and motor cortex. These regions show different patterns of activity during sleep, suggesting that procedural memory consolidation might occur through different mechanisms. Research has consistently shown that sleep enhances procedural memory performance. Studies where participants learn motor skills and then either sleep or stay awake typically find that those who sleep perform better on the skill the next day. This sleep enhancement of procedural memory has been demonstrated across a wide range of skills, from simple motor tasks to complex athletic movements. REM sleep appears to be particularly important for procedural memory consolidation. Studies using techniques that selectively disrupt different sleep stages have found that disrupting REM sleep can impair the consolidation of procedural memories while having less effect on declarative memories. This suggests that REM sleep may provide an optimal environment for the neuroplasticity processes that underlie procedural memory consolidation. The timing of sleep relative to procedural learning also appears to be important. Some research suggests that a nap that includes REM sleep after learning a new skill can enhance memory consolidation. This has practical implications for skill acquisition, suggesting that practicing a skill and then taking a nap might be more effective than continuous practice without rest. The processes that underlie procedural memory consolidation during sleep might involve the strengthening of neural pathways in motor regions of the brain. During practice, specific neural circuits in motor cortex, basal ganglia, and cerebellum are activated and modified. During subsequent sleep, particularly REM sleep, these neural circuits might be reactivated and further strengthened, leading to more stable and efficient motor programs. Sleep might also play a role in the automatization of procedural memories. Initially, performing a new skill requires conscious attention and effort. With practice and sleep consolidation, the skill gradually becomes more automatic, requiring less conscious attention and allowing for more fluid performance. This automatization process involves changes in how the skill is represented in the brain, from attention-demanding processes to more automatic processes. The enhancement of procedural memory during sleep might also involve error correction. When we practice a skill, we inevitably make mistakes. During sleep, the brain might replay these performance errors and work to correct the neural patterns that produced them. This error correction process could lead to more accurate and efficient motor programs, improving performance without additional practice. Dreaming might play a role in procedural memory consolidation as well. Some researchers have suggested that dreams sometimes involve rehearsing skills or movements learned during the day. This dream rehearsal might contribute to the strengthening of neural pathways involved in the skill, even though we're not consciously aware of this practice. The relationship between sleep and procedural memory becomes particularly interesting when considering complex skills that require both cognitive and motor components. Skills like playing a musical instrument or participating in sports involve complex coordination between perception, cognition, and movement. Sleep might help integrate these different components of the skill, leading to more cohesive and automatic performance. The study of procedural memory consolidation during sleep has important implications for education and skill acquisition. It suggests that interleaving practice with sleep periods might be more effective than massed practice. This approach, known as spaced learning, aligns with the brain's natural processes of memory consolidation and might lead to more efficient skill acquisition. Professional athletes and musicians have long recognized the importance of sleep for performance. Many report that they perform better after a good night's sleep, and that sleep deprivation significantly impairs their performance. These observations align with scientific research showing that sleep is crucial for the consolidation and enhancement of procedural memory. Sleep might also play a role in creative problem solving related to procedural skills. During REM sleep, the brain might explore different combinations of neural patterns related to a skill, potentially leading to insights or innovations in how the skill is performed. This creative aspect of procedural memory processing during sleep might help people discover more efficient or innovative ways to perform skills. The consolidation of procedural memories during sleep might also involve integrating the skill with existing knowledge and abilities. A new musical instrument skill, for example, might be integrated with existing musical knowledge, making it easier to incorporate the new skill into one's overall musical abilities. This integration process might occur during sleep through the coordination of different neural networks. As we age, the consolidation of procedural memories may change. Older adults often show slower acquisition of new procedural memories, but may be better at maintaining previously learned skills. Sleep patterns also change with age, potentially affecting how procedural memories are processed during sleep. Understanding these age-related changes can help develop more effective approaches to skill learning and maintenance throughout the lifespan. Understanding how sleep enhances procedural memory has practical applications for education, sports training, rehabilitation, and many other areas of life. By appreciating the importance of sleep for skill consolidation, we can develop more effective learning strategies and performance optimization techniques. Forgetting and memory selection represents one of the most fascinating and counterintuitive aspects of memory function. While we often think of memory as primarily concerned with remembering, the ability to forget selectively might be just as important for effective cognitive functioning. Sleep appears to play a crucial role in this process of memory selection, helping us determine which memories to keep and strengthen, and which to weaken or discard. The process of memory selection during sleep might seem paradoxical at first glance. Why would our brains work to weaken or discard memories we've worked hard to acquire? However, this process of adaptive forgetting serves several important functions. Our brains have limited capacity, and keeping every detail of every experience would quickly overwhelm our cognitive systems. By selectively preserving the most important information and discarding less relevant details, our brains create more efficient and usable memory systems. Research has shown that sleep helps to enhance the gist or essential meaning of memories while reducing details. When people learn a list of words and then sleep, they tend to remember the main themes or categories better than people who stay awake. However, they might remember fewer specific details about individual words. This pattern suggests that sleep might help us extract the most important information from our experiences while discarding less essential details. The process of memory selection during sleep might involve several mechanisms. Neural replay during sleep might prioritize certain aspects of experiences over others, replaying the most important elements more frequently. This selective replay could lead to stronger consolidation of important information, while less important information receives less reinforcement and gradually fades away. Another mechanism of memory selection during sleep might involve the integration of new memories with existing knowledge networks. When new information fits well with what we already know, it might be more easily integrated and thus more likely to be retained. Information that doesn't connect well with existing knowledge might be more likely to be weakened or discarded during sleep consolidation. The timing of memory selection during sleep might also be important. Research suggests that different sleep cycles might focus on different aspects of memory processing. Some sleep cycles might prioritize strengthening recently acquired memories, while others might focus on integrating those memories with existing knowledge or pruning less important information. This distribution of functions across sleep cycles could help optimize the overall efficiency of memory systems. The concept of synaptic homeostasis offers another perspective on memory selection during sleep. This theory suggests that the processes that strengthen synapses during learning lead to an overall increase in synaptic strength across the brain. Sleep, particularly slow-wave sleep, might provide an opportunity for downscaling synaptic strength to more sustainable levels. This process might preferentially preserve the most important or frequently used connections while weakening less important ones. Emotional factors might also influence which memories are selected for preservation during sleep. Emotionally significant experiences tend to be strongly encoded and might be preferentially consolidated during sleep. However, as discussed earlier, sleep might also help reduce the emotional intensity of these memories, making them easier to recall without being overwhelmed by the associated emotion. The process of memory selection during sleep might have important implications for learning and education. It suggests that not all study time is equally effective. Studying immediately before sleep might be particularly beneficial because the information will be fresh in the brain when sleep begins. It also suggests that the quality of initial encoding might affect which memories are selected for preservation, with strongly encoded information being more likely to survive the pruning process during sleep. The study of memory selection during sleep has led to new insights into how our brains organize and optimize memory systems. Rather than storing every detail of every experience, our brains appear to have evolved sophisticated mechanisms for creating efficient, organized memory systems that highlight important information while discarding irrelevant details. This selective process helps us maintain cognitive efficiency while still preserving the most important aspects of our experiences. Understanding how sleep contributes to memory selection can help us develop more effective learning strategies. It might encourage us to focus on the most important information during learning sessions, trusting that our brains will prioritize this information during sleep. It might also help us appreciate that forgetting is a natural and important part of memory function, not a sign of failure. As we continue to explore how sleep consolidates memory, we'll examine how these processes change throughout our lifespan, how we can optimize our learning and sleep schedules for better memory, and what future research might reveal about these fascinating processes. By understanding how sleep helps us determine what to remember and what to forget, we can develop greater appreciation for the efficiency and adaptability of our memory systems. Aging and memory consolidation represents another important area of research, as both sleep architecture and memory function change significantly throughout the lifespan. Understanding how these changes interact can help us appreciate the importance of maintaining healthy sleep habits throughout life and developing appropriate strategies for cognitive health as we age. One of the most well-documented changes in sleep architecture with age is the reduction in slow-wave sleep. Older adults typically experience less deep, slow-wave sleep than younger adults. This reduction in slow-wave sleep might be particularly relevant for memory consolidation, given the important role that slow-wave sleep appears to play in declarative memory consolidation. Changes in slow-wave sleep with age might partially explain some of the memory changes that occur in older adulthood. Older adults often report more difficulty learning new information and might show slower acquisition of new memories. These changes might be related, at least in part, to reduced opportunities for the types of memory consolidation that occur during slow-wave sleep. Sleep also tends to become more fragmented with age. Older adults often experience more nighttime awakenings and spend less time in continuous periods of sleep. This fragmentation can disrupt the normal cycling through sleep stages, potentially interfering with the coordinated processes of memory consolidation that require the proper sequencing of different sleep stages. The timing of sleep also changes with age. Many older adults tend to go to sleep earlier and wake up earlier than they did when they were younger. This shift in circadian timing, sometimes called advanced sleep phase syndrome, can affect how sleep interacts with daily activities and learning schedules. The coordination between learning and sleep might become less optimal when sleep occurs at different times relative to the learning experience. Memory changes with age are complex and multifaceted. While older adults often report more difficulty with certain types of memory, particularly episodic memory for recent events, they often maintain or even improve in other types of memory, such as semantic memory for general knowledge or vocabulary. These differential changes might reflect different patterns of memory consolidation during sleep for different types of memories. The relationship between sleep disorders and memory in older adults is particularly important. Conditions like sleep apnea, which become more common with age, can significantly disrupt sleep architecture and lead to excessive daytime sleepiness. Both the disrupted sleep and the sleep deprivation can impair memory function, creating challenges for cognitive health in older adults. Research has shown that treating sleep disorders in older adults can lead to improvements in memory performance. This suggests that at least some of the memory changes associated with aging might be related to sleep quality rather than inevitable brain changes. This insight offers hope for maintaining cognitive function through better sleep health. Lifestyle factors become increasingly important for sleep and memory health with age. Regular exercise, maintaining social engagement, and managing stress can all contribute to better sleep quality and might support better memory function in older adults. These factors might be particularly important given the age-related changes in sleep architecture. The study of sleep and memory in aging has led to important insights about cognitive health maintenance. Some researchers have proposed that sleep problems in older adults might be an early indicator of cognitive decline or neurodegenerative conditions like Alzheimer's disease. This suggests that monitoring and addressing sleep issues might be important for early detection and intervention for cognitive health. Interventions that aim to improve sleep quality in older adults might have benefits for memory function. These might include sleep hygiene education, treatment for sleep disorders, environmental modifications to support better sleep, and possibly pharmacological interventions when appropriate. Some research suggests that improving sleep quality might lead to measurable improvements in memory performance. The timing of cognitive activities relative to sleep might become even more important with age. Given the changes in sleep architecture, older adults might need to be more strategic about when they engage in learning activities to optimize memory consolidation. This might involve learning important information earlier in the day or taking naps that include the appropriate sleep stages for consolidation. The relationship between sleep and memory in aging also has implications for lifelong learning and cognitive engagement. Engaging in mentally stimulating activities throughout life might help maintain cognitive function, and getting adequate sleep might enhance the cognitive benefits of these activities. This suggests that lifelong learning and good sleep habits might work together to promote cognitive health. Genetic factors might influence how sleep and memory change with age. Some people might be genetically predisposed to maintain better sleep quality and cognitive function as they age, while others might be more vulnerable to age-related changes. Understanding these genetic factors could help develop more personalized approaches to cognitive health maintenance. The study of sleep and memory in aging represents an important area of research with significant implications for public health. As populations age worldwide, understanding how to maintain cognitive health through better sleep could have substantial benefits for individuals and society. This research highlights the importance of viewing sleep and memory health as important components of healthy aging. Practical applications for learning and memory represent one of the most immediately valuable aspects of sleep and memory research. Understanding how sleep consolidates memory can help us develop more effective strategies for learning, studying, and skill acquisition. These evidence-based approaches can improve academic performance, skill development, and everyday cognitive function. One of the most well-supported findings from sleep and memory research is the importance of timing study sessions appropriately. Studies have shown that studying shortly before sleep, particularly before slow-wave sleep, can enhance memory consolidation. This suggests that students might benefit from reviewing important material in the evening rather than pulling all-nighters or studying late into the night. Napping has been shown to be particularly beneficial for memory consolidation. Short naps that include both NREM and REM sleep can enhance the consolidation of memories learned just before the nap. This has practical implications for learning. Taking a brief nap after studying might be more effective than continuous studying without rest. The timing and duration of naps can be optimized based on the type of learning and individual sleep patterns. Sleep hygiene practices that promote good sleep quality can indirectly support memory consolidation. Creating a dark, quiet, cool sleeping environment, maintaining consistent sleep and wake times, avoiding caffeine, alcohol, and heavy meals close to bedtime, and developing a relaxing bedtime routine can all contribute to better sleep quality and, by extension, better memory consolidation. The spacing effect in learning. The finding that spaced study sessions lead to better long-term retention than massed practice aligns well with sleep and memory research. Spacing learning sessions across multiple days with sleep in between allows for multiple rounds of memory consolidation, each building on the previous one. This approach works with our brain's natural memory consolidation processes. The type of learning material can influence how sleep affects memory consolidation. Declarative information like facts, dates, or vocabulary might benefit most from sleep that includes adequate slow-wave sleep. Procedural skills like playing an instrument or sports might benefit more from sleep that includes adequate REM sleep. Understanding these differences can help optimize study strategies for different types of learning. The relationship between stress and memory consolidation suggests that managing stress around learning and sleep might be important for optimal memory performance. High levels of stress hormones like cortisol can interfere with both memory encoding and consolidation. Techniques like mindfulness, deep breathing, or exercise might help manage stress and create better conditions for memory formation and retention. Physical exercise has been shown to have both immediate and delayed benefits for memory and sleep. Regular exercise can improve sleep quality, which enhances memory consolidation. Exercise also increases levels of brain-derived neurotrophic factor, a protein that supports neural plasticity and might facilitate memory consolidation. Some research suggests that timing exercise to occur before learning might enhance initial encoding, while exercise after learning might support consolidation. The role of nutrition in sleep and memory consolidation is an emerging area of research. Certain nutrients and dietary patterns might support better sleep quality and cognitive function. For example, foods rich in omega-3 fatty acids, antioxidants, or certain vitamins might support brain health and memory processes. However, timing and balance are important, as eating too close to bedtime can disrupt sleep quality. Technology use, particularly close to bedtime, can interfere with both sleep quality and memory consolidation. The blue light from screens can suppress melatonin production and delay sleep onset. The stimulation from engaging digital content might activate the brain when it should be preparing for sleep. Creating a digital sunset, a period before bedtime when screens are turned off, can support both sleep quality and memory consolidation. The environment in which we sleep can influence memory consolidation. A bedroom that's cool, dark, and quiet promotes better sleep quality and might enhance the processes of memory consolidation. Some research suggests that certain aromas or environmental sounds might support relaxation and better sleep, potentially creating better conditions for memory processing during sleep. Understanding individual differences in sleep patterns and memory can help people develop personalized learning strategies. Some people are naturally more alert in the morning, while others are more alert in the evening. Working with these natural patterns, rather than against them, might optimize both learning efficiency and memory consolidation. The timing of learning relative to important events can be strategically planned. When possible, learning important information well in advance of when it will be needed, with adequate sleep for consolidation in between, can enhance retention. This is particularly relevant for students preparing for exams or professionals preparing for important presentations. As research continues to advance our understanding of how sleep consolidates memory, new applications and technologies are emerging. Some researchers are exploring targeted memory reactivation techniques that might enhance specific memories during sleep. Others are investigating whether certain substances or interventions might specifically enhance memory consolidation processes. Future directions in sleep and memory research promise to transform our understanding of these fundamental processes. Advances in technology and neuroscience are opening up new possibilities for studying sleep and memory, with implications ranging from education to clinical treatment of memory disorders. These developments may eventually allow us to optimize memory function in ways that were previously unimaginable. Advanced neuroimaging techniques are allowing researchers to observe the brain processes involved in memory consolidation with unprecedented detail. High-resolution functional MRI can track changes in brain activity during different sleep stages, revealing how different brain regions communicate during memory consolidation. These techniques are helping us understand the precise timing and coordination of neural processes that support memory. Artificial intelligence and machine learning are being applied to analyze complex patterns in sleep data and memory performance. These technologies can identify subtle patterns that might not be apparent to human researchers and might help predict which factors most influence memory consolidation in different individuals. This could lead to personalized approaches to learning and memory optimization. Wearable technology is becoming increasingly sophisticated in its ability to monitor both sleep and cognitive performance. Some devices can track sleep stages with increasing accuracy, while others can monitor indicators of cognitive function. These technologies might eventually allow for real-time optimization of learning schedules based on individual sleep patterns and memory consolidation needs. Pharmacological research is exploring compounds that might enhance memory consolidation during sleep, while existing substances like caffeine can improve alertness and some aspects of cognitive function. Researchers are investigating more targeted approaches that specifically enhance the neural processes of memory consolidation. These developments might have applications in education, clinical treatment of memory disorders, and age-related cognitive decline. Gene editing technologies are opening up possibilities for understanding the genetic basis of individual differences in sleep and memory. By studying genetic variations that affect sleep architecture and memory function, researchers might develop more personalized approaches to optimizing both sleep and memory processes. Virtual and augmented reality technologies are being explored as tools for both studying and potentially enhancing memory consolidation. These technologies could create controlled environments for studying memory processes during sleep or develop training programs that optimize memory consolidation through specific types of virtual experiences. Chronotherapy approaches are becoming more refined, with researchers developing personalized schedules for light exposure, activity, and rest that optimize both sleep quality and memory function. These approaches might be particularly valuable for people with disrupted circadian rhythms or those who need to perform optimally at unusual times. Brain-computer interfaces represent another frontier in sleep and memory research. These technologies might eventually allow us to directly observe and potentially influence neural processes during sleep. While this technology is still in early stages, it could eventually allow for unprecedented understanding and optimization of memory consolidation processes. The integration of sleep and memory research with other fields like computer science, physics, and mathematics is leading to new theoretical frameworks for understanding memory processes. Computational models of memory consolidation are becoming increasingly sophisticated, helping researchers test hypotheses about how different factors influence memory processing during sleep. As we continue to explore the fascinating relationship between sleep and memory, we're gaining increasingly detailed understanding of how our brains process and store information during the hours of darkness. This research is not just academically interesting, but has profound implications for education, mental health, cognitive aging, and many other aspects of human experience. Sleep well, dream peacefully, and trust that your brain is working diligently to process and store the experiences of your day. The memory consolidation that occurs during sleep is one of the most remarkable and essential functions of the human brain, a process that transforms the fleeting experiences of wakefulness into the lasting memories that shape who we are. Each night offers another opportunity for your brain to organize, strengthen, and integrate the memories of your day, preparing you to greet the next day with the knowledge and skills you've acquired. The journey of memory is continuous and ongoing, with sleep serving as a crucial bridge between new experiences and lasting knowledge. By understanding and respecting this process, we can work with our natural biological rhythms rather than against them, creating better conditions for learning, remembering, and growing. May your nights be restful and your days filled with the fruits of your brain's remarkable memory work.